our third speaker, and we're going back to the LHC, I understand correctly. So our third speaker is bringing us back to the LHC about the legacy that we have of 1.1 on thermodynamic operators.
So let's start with some basic facts. We know that within the standard model framework, the trilinear and the quartic vector boson couplings are completely determined by the H symmetry. Another basic fact is that by studying these kind of interactions, we can check additional confirmation of the standard model or find some new hints of new phenomena at higher scale. Also, another basic fact is that triple gauge couplings contribute to the boson production. To study these kind of problems, the physicists use the effective field theory approach, where basically we have an effective Lagrangian with the standard model part, and with another part with new operators that parameterize what we don't know from the high energy scale. So in the case of triple gauge couplings, the most relevant C and P conserving dimension 6 bosonic operators are this subset with the OW, the OB, the OBW, OPhi1, and OWW that have the gauge fields and the scalar field. When we introduce these on the Lagrangian, there will be shifts on the triple gauge couplings that are parameterized linearly by these new coefficients. The picture seems to be clear, but nevertheless, these people, Zhang and Dawson, concluded that not only triple gauge couplings, but also couplings between the gauge boson in the fermions can play an important role in the bounds of using the LHC data on triple gauge couplings, even taking into account the electroweak precision data. So we must enlarge the subset of operators with new ones that contain fermionic fields. So these fermionic fields will change the vertex of the Z couplings, the W couplings, and the Z with lattice. So our main goal will be using the LHC data 1 and study the impact of the fermionic operators on the triple gauge couplings bounds. So the recipe is the usual of picking the data from the collaborations, using the model with defined rules, doing all the simulation with MATGRAPH, with the detector simulation of Delphis, and always using the same kinematic distributions to validate our simulations from the collaborations. And then in the end, we can construct a chi-square function that contains the data from the LHC Run 1 plus the electroweak precision data that affects the new operators that we are including also. So, just to show you some results of the work, we can see that by including the new fermionic operators, there is a clear shift on the bounds of the canonical coefficients, like FB and FW. Regarding F triple W, there is no significant shift. Also, we can evaluate the effect of each of the new operators and in the canonical ones. So you can see, for instance, here on FP there is correlation between FP and this one, also with this one, or anti-correlation. Also regarding the FW, there is some correlation here and here, and a strong anti-correlation with this fermionic operator. As for F triple W, there is no anti-correlation with the new fermionic operators. So basically, the summary is that we could find new bounds for the canonical operators that we used to study in effective field theory to study the triple H couplings, and we see that with the new vertex between the H boson and the fermions, the limits on FP and FW change. As for the F triple W remains almost unchanged. So thank you.
One very good question. Don't be shy.
So thank you, it's very interesting. The question would be, why did you choose the 8TV data set, and to extend this, is the 13T data set maybe not fully mapped out yet?
The surfing.
The data that you chose to do your constraints. You used the run data.
I used run because the available for the second run is too poor to study this.